An assertion from teacher Carlos. Straight to the point, Durham College. I've committed my whole profession to fostering a particular hypothesis about the universe. Then this happens. The hypothesis is being addressed. I embrace this challenge since it is through such scrutinizing that we advance and gain ground in science. The James Webb Space Telescope is essentially upsetting some lengthy-held convictions in cosmology that have been acknowledged as truth for a century. Another ultra-profound picture has uncovered that we have made blunders in space science. The telescope, which was planned to uncover the principal stars of the universe, is rather difficult. The past perspective may present a totally new logical worldview. Not all specialists are troubled about these new discoveries. Numerous researchers are inviting these advancements since it has for quite some time been apparent that there were issues with our past hypotheses. The irregularities in estimating the universe's development rate alone ought to have alarmed scientists quite a while back. Anyway, rather than correctly deciphering these admonitions, many clutched obsolete hypotheses. The cosmic microwave background radiation, CMB, which is the most seasoned light in the universe, was made about 380,000 years after the Big Bang, when the universe had cooled adequately for electrons and protons to form stable hydrogen molecules. This change, known as reionization, made the universe transparent to light. The CMB was first identified in 1964 by American physicists Arnold Penzias and Robert Wilson while they were chipping away at new receiving wire innovation. They experienced a determined commotion coming from each bearing in the sky. This discovery was at first thought areas of strength for the Big Bang hypothesis. Penzias and Wilson were granted the Nobel Prize, and their finding turned into a foundation in the history of astronomy. The CMB likely gives a preview of the early universe, with minuscule temperature changes offering basic bits of knowledge into the circumstances not long after the huge explosion. Researchers utilized the CMB as a dependable engraving to quantify crucial parts of the material universe, including the universe's development rate. Edwin Hubble had proactively made such estimations in the last part of the 1920s. He observed that far-off worlds are getting away from us every which way, and that their speed connects with their distance, which is now known as the Hubble regulation or the Hubble steady. Despite the fact that Hubble's estimations were not as exact as pivotal, they were foundational when the CMB was found. Analysts recalculated the extension rate, finding it essentially lower than Hubble's starting assessment. Subsequent recalculations utilizing type Ia supernovae as standard candles gave a more precise estimation. However, errors remained. The distinction in extension rate estimations has been known since the 1990s. Analysts have thought that there could be issues with the CMB data estimation techniques or the idea of universal extension. This disparity, known as the S8 tension or Hubble tension, demonstrates that our comprehension of the universe may be generally imperfect. Since the James Webb Space Telescope began its activities, it has provided astonishing data that could assist with explaining the issue. Galaxies so old and mature that their arrangement ought to hypothetically originate before the Big Bang are challenging old logical speculations. Astronomy currently faces what is thought to be the best emergency in current stargazing. The extension pace of the universe and the theory of how things came to be are under a magnifying glass. Webb's pictures uncover a universe that varies essentially from past models. The S8 pressure filled in as in starting admonition, and scientists who still cling to obsolete speculations now face a situation. Numerous researchers are wrestling with the acknowledgement that our knowledge of the universe might be deficient. This vulnerability has left numerous analysts pained and confounded. To address this emergency, we must comprehend how science works. Theoretical researchers utilize a mix of numerical models, observational information, and logical thinking to reach inferences. Their insight comes from noticed peculiarities, test results, and hypothetical analysis. The term hypothesis itself suggests builds and thoughts, as opposed to outright insights. Our reasonable knowledge comes from pictures given by telescopes, sound waves, and radiation caught by radio telescopes, as well as information from neutrino and gravitational wave identifiers. The James Webb Space Telescope permits us to separate the most established light into individual frequencies and analyze it in exceptional detail. It can show which components were common in galaxies more than 13 billion years ago, the mass held inside them, and the quantity of stars present. However, Webb's pictures might have impediments. For example, it can't necessarily distinguish between galaxies and black holes that discharge comparable brilliance due to monstrous accumulation plates. Our logical comprehension has advanced to acknowledge numerous possibilities as bits of insight and has frequently excused other option clarifications. New discoveries from the James Webb Telescope offer vital hints that may lead to replacing old hypotheses with new bits of insight. Researchers are at present wrestling with these disclosures, which appear to be so exceptional that finding new clarifications is challenging. The most recent revelations are shaking the establishments of physics, causing concern among a large number of analysts. Physics lessons today are still intensely affected by Isaac Newton's 17th century work. For 400 years, his laws of movement and gravity have provided the foundation for understanding the physical world and the universe. Newton's regulations make sense of object developments under regular circumstances effectively on Earth. However, in space, his thoughts required extension, generally achieved by Albert Einstein in the mid-20th century. Einstein's unique hypothesis of relativity, published in 1905, revolutionized the understanding of existence, demonstrating their relativity to the spectator's movement. His general hypothesis of relativity, published in 1915, extended these ideas with numerical confirmations of gravitational peculiarities based on spacetime curvature caused by masses like stars or galaxies. While Einstein's speculations were lucid in numerous areas, he recognized their impediments and sought a binding unifying equation without success. No specialist has yet prevailed in this attempt. It is fascinating to consider where missteps could lie. Michio Kaku, a conspicuous American astrophysicist, suggested that addressing this issue could lead to a Nobel Prize. We want to research what realities researchers could have ignored, whether there have been misinterpretations of peculiarities, or if telescopes may be at fault. Dark matter and dark energy are top suspects in the cosmological emergency. Current models suggest that dark matter and dark energy together account for around 95% of the universe. Yet, neither has been straightforwardly noticed or demonstrated to exist. They may not exist at all, or perhaps have properties we don't yet comprehend. One thought being discussed is that these dark parts' properties may have evolved over time, potentially showing some type of insight. Gravity, which should cause attraction through mass or spacetime curvature, has not been conclusively demonstrated. Despite the fact that spacetime shape ideas, largely from Einstein, have been validated various times, we can't altogether preclude the possibility that gravity has unexpected properties compared to what we accepted, or that another effect causes gravitational attraction. Over the years, certain qualities in cosmology and astronomy have been established as vast constants, accepted to generally be solid due to their steadiness. Computations suggest that little varieties in these constants could give new experiences into the universe and make sense of peculiarities. Without dark energy, it is likewise conceivable that our translations of light's shift have been erroneous, prompting wrong distance estimations and galaxy ages. Maybe our assumptions about the universe's underlying circumstances were imperfect, or we misjudged the cosmic microwave background radiation. It may indeed even be that the universe doesn't begin from a solitary starting point, testing the theory of primordial cosmic detonation. Notwithstanding our innovative headways, minor mistakes in the Webb telescope or other observational devices can't be precluded. Specialists and researchers have recognized that blunders in instrumentation, data handling, or translation are generally conceivable. The continuous reassessment of cosmological speculations highlights an essential part of logical advancement: the capacity to adjust and advance our understanding considering new proof. The James Webb Space Telescope's perceptions are something other than a mechanical jump. They represent a significant moment in our journey to unravel the universe's secrets. As we grapple with these disclosures, it's essential to recognize the broader context and ramifications of such logical progressions in the domain of cosmology. The method involved with refining hypotheses is frequently driven by the need to accommodate perceptions with hypothetical models. The disclosure of startling peculiarities or irregularities in laid-out hypotheses can be disrupting. However, it likewise presents a valuable opportunity for logical development. Theoretical models in cosmology are developed to provide a lucid framework for understanding the universe's beginnings, construction, and advancement. However, as new information arises, These models should be tested and, if vital, revised to accommodate new insights. One huge area of center is the concept of dark matter and dark energy, which are vital to contemporary cosmological models. Dark matter, an undetectable type of issue that doesn't discharge or absorb light, was proposed to make sense of disparities between noticed galaxy revolutions and the mass anticipated by noticeable matter alone. Additionally, dark energy was introduced to represent the noticed sped-up development of the universe. Regardless of their critical roles in current models, both dark matter and dark energy remain confounding. Efforts to straightforwardly identify dark matter through tests on Earth have so far been ineffective, driving scientists to explore elective speculations and conceivable outcomes. The test of grasping dark matter and dark energy is compounded by the immense scope engaged in cosmological studies. Observations of far-off galaxies, cosmic microwave, background radiation, and other cosmic peculiarities provide circuitous proof of these components. However, their nature remains elusive. This vulnerability has prompted researchers to consider a range of speculations, from modifications to existing hypotheses to completely new principles. For example, some hypotheses suggest that dark matter could be made up of more exotic particles than previously suspected, or that dark energy may be a sign of a new fundamental force. Another, captivating part of cosmological exploration is the investigation of cosmic inflation. This hypothesis suggests that the universe went through a rapid expansion in its earliest moments, prompting the enormous scope structure we observe today. While inflationary theory has successfully explained many elements of the universe, such as its consistency and evenness, it also presents inquiries about the nature of the inflationary period itself. Later observations that challenge laid-out models of inflation could prompt updates in how we might interpret the universe's initial history. Moreover, the quest for extraterrestrial life continues to be a significant driver of galactic exploration. The discovery of exoplanets, planets circling stars outside our solar system, has opened up new avenues for investigating the circumstances necessary for life. Advances in telescope technology, such as the James Webb Space Telescope, enable researchers to analyze the atmospheres of these exoplanets for potential biomarker signatures. The chance of finding life beyond Earth has significant ramifications for our understanding of the universe and our place within it. Regarding theoretical physics, string theory and quantum gravity address two prominent approaches to unifying our understanding of the fundamental forces. String theory proposes that the essential building blocks of the universe are not point-like particles, but instead one-dimensional strings vibrating at various frequencies. This theory aims to accommodate general relativity, which describes gravity, with quantum mechanics, which governs the behavior of particles at the smallest scales. Despite the fact that string theory remains highly theoretical and mathematically complex, it has inspired better approaches to studying the nature of space-time and matter. Quantum gravity, on the other hand, tries to develop a framework that combines the principles of quantum mechanics with those of general relativity. One of the main candidates in this field is loop quantum gravity, which posits that spacetime itself has a discrete granular structure at the smallest scales. This approach aims to resolve the apparent inconsistencies between the smooth spacetime of general relativity and the probabilistic nature of quantum mechanics. The transaction between theory and perception in modern cosmology highlights the dynamic nature of scientific inquiry. As our observational devices advance, our capacity to test and refine theoretical models becomes more precise. For instance, gravitational wave astronomy has provided a new means of concentrating on peculiarities like black hole mergers and neutron star crashes, offering insights into the fundamental nature of gravity and the behavior of matter under extreme circumstances. These revelations have not only confirmed expectations of general relativity, but have also opened up new inquiries concerning the nature of spacetime. In parallel, the field of astrobiology investigates the potential for life in the universe by concentrating on extreme conditions on Earth and mimicking conditions on other planets. Investigation into extremophiles, organisms that flourish in harsh conditions such as extreme heat, pressure, or radiation, provides insights into the types of conditions where life may exist elsewhere. This interdisciplinary approach, which combines biology and planetary science, enhances our understanding of the potential structures and environments of extraterrestrial life. As our insight into the universe expands, so too does our appreciation for the complexity and interconnectedness of cosmic phenomena. The ongoing investigation of crucial inquiries about the nature of reality challenges our assumptions and drives us to seek deeper understanding. Every disclosure, whether it affirms existing hypotheses or proposes new avenues of inquiry, contributes to a more comprehensive perspective of the universe. In summary, the reassessment of cosmological speculations considering new perceptions is a testament to the resilience of the scientific method. The James Webb Space Telescope and other advanced observational devices have provided extraordinary insights into the universe, prompting researchers to revisit and refine long-held theories. This interaction of continual inquiry and transformation is essential for advancing our understanding of the universe and resolving the significant inquiries that lie at the core of cosmology and astronomy. As we continue to explore the universe, we remain engaged in a quest for knowledge that not only seeks to answer fundamental questions, but also inspires future generations to push the limits of human understanding.